Yeah, welcome to this talk about computational analysis of music audio recordings. I will talk about corpora, concepts and algorithms, and as you may expect, there is some focus on Western classical music because that's the focus of my work and also my group now. Let me quickly add to the nice introduction that Martin already gave. I studied physics initially in Würzburg, where I'm ended up now, and music composition at the University of Music, same city. Then did my PhD with the semantic music processing group in Ilmenau, and then joined Meinrad Müller's lab in Erlangen for a postdoc of almost 8 years. During that time, I did a break and visited Geoffroy Peters' team at Telecom Paris. And now, since already more than 3 years, I'm associate professor with the Computer Science Institute and the AI Center CAIDAS in Würzburg, not that far from Erlangen and also close to Frankfurt, so quite in the center of Germany. And since 2 years, I'm also leading a junior research group. That's a special type of funding for a larger group by the German funding agency. And there we focus on cross-version music analysis. I will later talk a little bit more about that. This is my research group at the moment, and many of the results that I present today are done together with this group, and I'm very happy to being able to build up such a nice group. Let me quickly explain what we are working on and what the structure of our group is. So we as Computational Humanities Group are belonging to various institutions at the same university. The Computer Science Institute on the one hand side, the Faculty of Humanities, and then also the Center for AI and Data Science, which is a interdisciplinary center bridging AI and application domains, and another interdisciplinary center which is more focused on the specific interaction between AI, computer science, and the humanities. And this center also has obtained a very nice building, inaugurated 3 years ago, where my group is sitting and where we could build up a nice studio for audiovisual culture where we can do recordings. What is computational humanities? Of course, it's highly interdisciplinary, having computer science and engineering on the one hand side, humanities on the other hand side, and the study of cultural data, music, literature, fine arts, and so on is at the center. This involves different modalities such as text, if you think of literature, symbolic data of different kinds, image data, if you think about fine arts, of course, video, movies, stage performances, and audio data in music. My group is focusing on this lower part, so that's what we call raw data, where we don't start from an explicit computer readable format, as the case in text, but from some raw pixel, waveform, whatever video frame information, where we need specific algorithms to have interpretable representations to start with. And of course, there's a focus on music and audio. And by the way, also for music, we have all these modalities. We have symbolic data, of course, for score sheet music. We have also text data, if you think about lyrics, libretto. We have images, sheet music scans, but also album covers. We have video, soundtrack of movies, film performances of opera or musical performances or video clips of pop songs. And of course, we have audio, and audio is a very important source because for many music styles and traditions, it's the primary source because they are not based on written music, such as traditional music of many cultures, improvised music as in jazz, and electronically produced music. So this audio data and this other type of data allows for computational musicology studies, and the big the great opportunity here is that we can build new strategies for musicology that are to some degree more objective. So we can measuring things without involving human interpretation in the first place. Of course, we will need it later. And it's scalable to arbitrary large databases. And that's a limitation of classical musicology. You can never listen to an arbitrary number of pieces. And as said, also computational musicology is very interdisciplinary. And there are three main components, if you want, that play together in this field. One is the corpora, the data. We need good corpora. Xavier has written a great paper about that that I often involve in my teaching as well. This comprises the field of digital edition, so the quality of the data, and also the technical side of data types, which types of data, symbolic, image, audio, we involve. Then we have the concepts. This is the music knowledge that we need to analyze the data. So the parameters, the questions that we ask about the music, and the terminology, for example, harmony, rhythm or meter, form and structure, or the aspects of interpretation and performance. And the third component is the algorithms. So the methods with whom we analyze the corpora, and they relate to the concepts and then use useful techniques from signal processing, from pattern recognition, deep learning, and AI to analyze the corpora with respect to the concepts. And if these things come together in a fruitful way, we can do nice corpus studies. And this involves different tasks. We need to represent the corpora. We need to do hermeneutical interpretation. We need the music theory concepts to do a suitable modeling, to quantify some concepts. And this allows us to do suitable measurements. We also need to code our data to do that. That often involves something like synchronization, bringing time access together, or even transcription to go, for example, from audio to a directly human readable format. And I will talk about a couple of different applications, case studies that we did that involve different corpora, different concepts, and different algorithms. And these algorithms and also the concepts in music are challenging. And one reason why they are challenging is that they are hierarchically related to each other. So let's consider the field of harmony and tonality, for example. We start on the note level where we have the information on individual pitches, note events if you want. We can induce higher level segments such as chords, which are already somewhat more abstract. Some pitches belong to the chords, others not. We can find coarse scale segments such as local keys, or we can find a single label for a whole piece or movement that we denote as global key. So something like symphony in C major. And since both the global key can be C major, the local key can be C major, and the chord can be C major, you already see there is some ambiguity and challenge involved. So we use the same terminology for different things that are, however, hard to separate from each other sometimes. Okay, I will talk about three selected tasks regarding this hierarchy, going from bottom to top. And we will start by talking a little bit about extracting pitch information from audio. And for this, I will quickly talk about a data set that we built some years ago in Erlangen based on many years of previous work by different people. And it's centered around Franz Schubert's song cycle Winterreise, which is by itself a composition based on 24 different poems. So we have 24 different songs. And we have different data types, modalities. We have the lyrics, the text, which is mainly based on what the poet, in this case Wilhelm Müller, wrote. We have what is attributed to the composer, Schubert, which is score data. And we have it in different formats, image, symbolic, MIDI. And we have 9 recorded performances, which means audio recordings, capturing performances by different singers and pianists. And we can use such a data set to develop models for extracting pitch information. So what we want is we have an input audio recording as the one indicated by the waveform above, and we want to analyze which pitches are active over time. Let's simplify it a little bit, talking about pitch classes only, ignoring octave information. Okay, and this pitch class information is traditionally called something like chroma features, chromograms in MIR, and you can extract it with simple time frequency transforms and some post-processing, for example, based on the constant Q transform, and you get some coarse representation, which has some similarity to this already. But you see there are a lot of problems. We have onsets that result in vertical lines, transient components. We have the vibrator of the singer, which spans across neighboring pitch class bands, and we have a high noise level in general. So what we try to do is to improve such representations using deep learning with a rather small, just 50K parameters, a convolutional neural network with a very strong musically informed structure based on Rachel Bittner's harmonic CQT, where the convolutions span across harmonics, then doing some pitch filtering, some binning, time reduction, and chroma reduction in just 6 different layers. And training this network, we can now make use of our multimodal dataset because we have scores. And we can align, synchronize these cores to the time axis of the individual audio recordings, and then do a frame-wise loss to train this network. And the result is like that. So you saw it's a strong improvement. We can get rid of many of these transient signals and learn a network that predicts the pitch classes more or less as they are written in the score. And there is a challenge involved because this alignment is of course difficult and is also sometimes not unique. The singer may change at a different time than the pianist and so on. So to overcome this problem, we proposed in some works to use soft alignment loss for training based on the CTC idea. But if we want to train this for pitch class representations where we have multiple pitches active at the same time, we need a multi-label variant of this. And for this, we adapted some loss proposed for document analysis and applied it for this case of multi-pitch or pitch class estimation. And it actually worked quite well. So we can also train this without explicit alignment. And that's the direct comparison. So if we compare the annotations, so the target as it is derived from the score, with the different computed representations, we can compute the cosine similarity, and we see this is quite high for the trained variants, a little bit higher for supervised training, and much lower for the signal processing variant like the CQT. Yeah, and this is a nice way how you can use deep learning also for musicology. The result is still completely interpretable. We don't train an arbitrary embedding, which is just whatever 128-dimensional vector, but we can still interpret it and further process it. And this is what we want to do in the next applications. So let me go to another task, which is on a coarser temporal level, local key estimation. So we again want to start with the Schubert-Winterreise dataset. And this dataset does not only have different modalities, capturing, so to say, the raw data of these songs, but we also have annotations on various musical aspects. For example, we have measure positions, which allow us to have some ground truth alignment between the different representation. We have chord annotations, and we have local key annotations, for example. And we can use these local key annotations to, again, train systems to do this task, to take the audio as input or some time frequency transform of it and predict the local key. And we can do this in a two-step approach, for example, doing pitch class estimation, and then traditional like dynamic programming model like an HMM. together with some Gaussian modeling, or we can do it with deep learning again, using a convolutional network, also based on some CQT input. And we will later compare these two approaches. So the nice thing of our dataset is now that we can exploit the existence of several performances, we call them versions, to learn more about our algorithms. And there are three principal possibilities how to split our data. The first one we call a version split. In this case, we use all songs for training. So we can, so to say, overfit to the songs. But in just some of the versions, we use all songs in another version for validation. And we use again all songs for testing, but in unseen versions. So this tells us how well do our models generalize to different acoustic conditions, different singers, maybe different interpretation styles. The counterpart would be the song split, where we train on all versions, but only of specific songs. That means we overfit to the acoustic conditions, but we need to generalize to different musical content. So we have another song for validation, and we have yet another set of songs for testing. And we can do an intersection of these splits, which then lets us just use a subset of the data. So we can train on some versions of some songs, validate on other songs in other versions, and test on yet another set of versions of yet another set of songs. So this is, so to say, the most realistic scenario. Both the acoustic conditions and the musical songs are not seen, but of course they are from the same composer, so it's somehow as very similar music. Somehow a best case scenario for machine learning, because in machine learning you assume that your application domain is from the same probability distribution, and that's the case here. Okay, so how does that look like if we evaluate our two models in these different splits? I will start with the strict split, the so-called neither split, where neither the songs nor the versions are known to the model. And we see there is actually not that much difference between the traditional model, the HMM model, and the convolutional neural network. We see that the standard deviation across versions is smaller than the one across songs. So the acoustic conditions seem to have less influence than the music itself, the song. If we go to the song split, the situation is quite similar. The HMM is a little bit worse, so it could exploit the knowledge of the versions, but both are not great. But it changes if you go to the version split, where the models know all the songs, just in different performances. And here the CNN is much, much better. So reaching 95%. So that means what the CNN could really exploit is its knowledge of the music. So it knows the annotations. They are derived from some musicologists annotating the score. And it doesn't really matter for the CNN if it has seen the specific version, the specific performance. It can generalize well. And this is very interesting. And this lets us understand better what these models, especially the black boxes that we use in deep learning, are doing. And based on this idea, we have a large project going on. This is this Noeta research group I talked about, which builds on this cross-version approach, extends the version idea to not just performances, but also different modalities, also arrangements, different instrumentations, and so on, to systematically study what our MIR models have learned and what they have not learned. And I think some of you were at ISMIR. We have some work already presented there. We can also exploit this cross-version nature of our data sets for training, for semi or self-supervised training without having explicit labels and so on. Okay, but let's come back to the local key task. We looked a little bit deeper what happens there and analyzed the musical types of errors that occur in this scenario. And we found that almost all the errors that occur in these less well-performing models are musically close. So the predicted key is close to the annotated key. And close means either it's a relative key, like C major versus A minor, so same scale more or less. It's a parallel key like C major versus C minor, or it's some kind of fifth related key. So all those keys differ by at most one accidental, so to say. They have key signatures, but they're very similar. And together they explain almost all this performance gap. So the model is not making silly errors. It's not transposition error or tuning error. It's really a musical error. So that means we need to look closer. And if these keys, these errors are musically maybe ambiguous, then the next question is, what would different annotators say about these key annotations? And that's what we do. So the Schubert dataset also comprises two further local key annotations by different annotators that even knew the others' annotations, but because of their music theory teaching or some also room for interpretation, chose different key labels. And if we now take the model trained on one annotator, in this case it's trained on annotator 3, and evaluate it on the annotations by other annotators, the results go down, especially for this well-performing CNN. So for annotator 2, it drops below 90. For annotator 1, it drops almost to 80. So most of this performance gap is gone if you have a different musicologist annotating the key here. And these are all experts, so it's not the quality of the annotations, but rather the music theoretical perspective or school, let's say. So this means the A3 model has not just overfitted to the songs of the Winterreise, it has overfitted to the way a certain musicologist has annotated local key in these songs. And yeah, this is of course an important message, because then we don't need to go for the 100% in this task. So if we go for a direct comparison, pairwise comparison of these annotators, they only agree for 80 to 85% of the time on the key. And the times, or in the situations that they don't agree, they usually are in some close musical relationship. So for example, one annotates the relative key to the other one. And for comparing all three, so the number of frames where all three annotators agree, we are down to something like 76%. So that's really low. And there is a reason for this. And for this, I want to go into a specific example, a passage of song number 19 called Täuschung. And here we have a representation where we show how many versions are different from each other and what's the, so to say, the error or the difference that they are to each other. This is the score, and let's quickly listen to this example.
Ach, wer dich so elend ist, gibt gern sich in der bunten List, die hinter Eis und Nacht und Graus in Weiß dein helles.
Okay, so we are in the context of A major, that's clear, but there are definitely some chords that don't belong to A major. And what our model predicts is indeed some different keys. It predicts A minor for these two measures where we definitely have an A minor chord, but the question is if we also have an A minor key for only two measures, and then it predicts E major. One annotator, that's the one against which this is compared here, predicts A major as the key all the time. And that's not because this annotator doesn't know that we have A minor here, because the reason is that this annotator chose a different level of hierarchy. So the definition of a key is that you have a tonal center which with you could stop the music at a certain position. And the question is, can we stop in an A minor chord here, or do we still have some A major context that the music is resolving to? And the annotators disagree on that. So some say we have still A major, some say it's already strong enough to have an intermediate key here. So it's difficult to resolve this hierarchical problem. And that's the reason for this ambiguity here. And this is not really possible to resolve. I would not say that one or another annotator is more correct than the other one. And because of that, in many of our interdisciplinary projects, we take a different approach. We don't try to predict or classify the local key as a one class or multi-class classification problem, one label problem, but we try to measure what's going on in tonality in a softer way. This is computationally much more simple, but it allows for some interpretability by the musicologists. And I want to show how we do this at the example of Choral by Johann Sebastian Bach. And what we now do is we simplify the local key task a little bit. We go from the 24 major and minor keys to just the 12 diatonic scales, which is more or less the information of the key signature. And we call it with a neutral terminology. So +1 is the diatonic scale. So the 7 notes that can be notated with 1 sharp. -2 is the one with 2 flats, and so on. So you get the idea. And we want to analyze this choral from St. John's Passion by Bach in E major. This is the waveform, and we start again with a chromogram, some pitch class representation of this choral. Okay, so you already see we have some pitches that have more energy, like the E, the F sharp, G sharp, or the B. And we now will exploit this information and first go on a coarser temporal scale, because local key is something that spans a certain time, of course. So we go from this 10 Hertz resolution to some coarser resolution. We then rearrange this diagram from a chromatic ordering to a circle of fifth based ordering. So two pitches that are a perfect fifth apart, like E and B, now become neighbors. So they are next to each other now. And you see with this step, most of the energy is already concentrating in a part of this reordered pitch class representation. And then we also know that 7 neighbors in this representation form one diatonic scale, like these 7 ones would form the 5 sharp scale. And we just multiply the values to get some joint probability, normalize this, and get, so to say, some probability for the most likely diatonic scale at each of these coarse scale timeframes. So this is the probability for the 5 sharp scale. This is the one for the 4 sharp scale. And we have other ones. And this gives us a nice modulation diagram. What's the rough tonal content? It's not a key representation anymore. Is over the course of the time. And the nice thing is now we don't have to do hard decisions. We can have several non-zero probabilities, and often they occur for neighboring scales because of the ambiguities that we just saw in the local key task. Okay, so you nicely see this modulation from the global key to the upper fifth key, the dominant key, and then some more chromatic things are going on here. And this is nicely shown by these non-zero probabilities for a couple of scales. And here we don't really see that one of these scales is the correct one, but we see there's something non-diatonic, something more complex going on. And this is already also an interesting information for musicological research. Okay, I mean, this is somehow easy to analyze for a 1-minute choral, but this choral is part of Bach's St. John Passions, which spans more than 2 hours of music. So let's compress this choral a little bit. So this is the choral again, compressed a lot, and put it into the context of the whole work. So this is the roughly 2 hours of the St. John Passion. And you see this choral is quite at the center, both in terms of the numbers, it's around 40 different numbers, areas, recitativos, choruses, and so on. And also content-wise, it's kind of the center of the plot. And we see there is some symmetry. So the passion starts in the flat region around G minor, ends in C minor and E flat major. And yeah, we go up and down, up and down. And actually this E major is kind of the top of the passion. And that's very interesting also because E major was connected in Bach's time to the topic of death. And of course, the passion has to do a lot with death. And we see there is some symmetric structure around this choral, also tonality-wise. So for example, we have around this choral, like 2 numbers before, 2 numbers after, we are more in the flat region. Like we have C minor here in number 20. And we have G minor with 2 flats here in number 24. So this is information on the tonal symmetry of the work. And then the next step would be to connect it also to motivic things, because Bach also reuses some motivic ideas with different text across the passion. For example, one of the choruses before this choral, this one, is then reused in a different key after the choral. And now the visualization lets us give an insight into the somatic structure. And for this, it does not really matter what is the exact key here. If we are exactly in 3 flat or 2 flat, we already see there are some coarse tonal regions that are approached and also kept for a number of numbers, different areas, recitativos. And this is a very interesting insight that this visualization can provide. And since this seems to be useful for large-scale works, we applied such ideas to one of the most large-scale work in musicology or in Western classical music, Richard Wagner's Ring Cycle. This is an interdisciplinary project that we started in 2014, before I joined Meinhard Müller's lab, and went on for around 10 years in 2 phases, ended last year, and is dedicated to concepts for the large-scale analysis of harmonic structures in direct collaboration with historical musicologists in Saarbrücken, University of Saarland. And we, as one of the major endeavors in this project, we worked on a dataset and published this dataset on Wagner's Ring. And this work comprises 4 whole operas, Das Rheingold, Walküre, Siegfried, and Götterdämmerung, usually played on 4 consecutive evenings, subdivided into 11 acts in total. And each of the acts has a contiguous measure count from measure 1 to whatever 1000 something. So in total, it's almost 22,000 measures. You all know excerpts of this music, for example, the famous Ride of the Valkyries. Okay. Let me quickly stop this. Okay, so our dataset comprises the musical score. It comprises 16 different performances of the full ring cycle. For copyright reasons, we can release only 3 of them, but the other ones are commercially available. And in total, this is more than 200 hours of music. Okay. We have also annotations for this. So we have measure positions. 3 of these performances, we have manual measure annotations from 2 different annotators. And then we have the note events, we have singing regions, we have time signatures, and we have key signatures. And for example, this is how the measure positions look like. Yeah. And we will now use, for example, these key signature regions to derive some interesting visualizations. So what we do now is basically the same that we just did for Bach's work. We analyze the probability of these different diatonic scales over the course of such an opera act, in this case, the first act of a D Walküre. It's analyzed based on deep pitch class features, as I explained in the first part, and it shows us to which degree these 12 different diatonic scales are prominent. The time resolution is much coarser. It's something like 64 measures. So it's really the coarse scale evolution, but we see this is not random. We start in some minus regions and then have some modulation phases. And what we did in one previous work is we compared how different is this if we do it from pitch classes derived from some score. So this is the deep learning based one. We have one from the score data, and we have one based on classical signal processing, and we can compare them with a color scheme, like a visual overlay technique. So if we have the isolated measurements based on these 3 different representations, we get these colors, cyan, magenta, and yellow. And if they are occurring together, we get these mixed colors. Like, for example, the score and the deep learning together would yield this green. And if all 3 agree, then they add up to black. And what we observe is that either all 3 representations agree, then we have black, or we have green and magenta. So green means that that the score and the deep learning based approach yield the same result, but the signal processing one has a different result. Mostly it has several probabilities for different scales. And that's promising. That means that the deep learning based chroma feature helps us a lot to get closer to the result that we would get when using the pitch classes from the score. So we can close this gap to a certain degree. But now we still have this simple measurement of diatonic scales. What is interesting is to compare this with other perspectives on tonality in the ring. And there is not really a state-of-the-art local key annotation because it's very complex to annotate local keys for Wagner. We would get agreements much lower than for Schubert. But we can derive some representations from 2 other sources. We can, for example, just visualize the key signatures that Wagner has chosen in the score, like when he has written 3 sharps, when he has written 1 flat, because we can map it to the same representation space. And we found a very old, but still interesting annotation by a musicologist from the 1920s. And this is a rather idealistic annotation based on some idea of modulations in Wagner, which is still under debate in musicology. And we now use the same visualization technique to visualize these 3 perspectives with different colors. So now the cyan one is the computation measurement that we just looked at based on deep learning pitch class features. The magenta is based on the key signature regions that Wagner wrote into his scores. And the yellow one is these old musicologist annotation by Alfred Lorenz. And that's what we get for this act. And we see some very interesting details. So there are quite some regions, especially in the beginning and in the end, and also in some scenes where they all three coincide. And then there are some scenes where we have an interesting pattern. For example, this scene 3 here. In the beginning and in the end, they all agree. In the middle, this musicologist stays in the same key or the same tonality, but the other two, the key signatures that Wagner notated and the computation measurement, indicate a modulation that is then going back. So that already points again to a different choice of hierarchy. So Lorenz, the musicologist, stayed on a coarser level. He says the base key of the scene is whatever, -1, D minor. I stay on this. And the measurements are on a more local level. They indicate there is some modulation. And this also is the case for Wagner's key signature. So he also changes key signature at this passage. The computation measurements even shows us some transitions. So it seems to be a gradual modulation here. And then also we have some different keys when modulating back. And this is an interesting visualization because rather than deciding what is the correct key, we see a more complex picture of tonality. So we see there is some base tonality and we see there is also some deviation. And the more deviation we have, the more complex is a scene harmonically. The more agreement we have, the more stable is the harmony. And this can, of course, be related to the plot and discussed regarding Wagner's conception of his music dramas. I want to quickly, okay, and then we do this for the whole ring. No time for discussing this now. This is the full opera where we have then even less agreement. Last opera, we are in the process of publishing a paper on that. It's still under review. But I want to close my talk going to an even coarser level. We now looked at one of the largest works in classical music, but of course the strength of these computational methods is to go to whole corpora, many pieces of music. And also here we can exploit our pitch class representations. For example, if you look at the global pitch class distribution, so how often the different chromas or pitch classes occur, again, ordered on the series of fifth, we see some characteristic patterns. Like, for example, here we have an orchestra suite by Bach. Now we have a symphony by Mozart, a symphony by Brahms, and in the 20th century, Anton Webern, we also observe something like that. So that's a dodecaphony, 12-tone music. So, of course, no surprise, but it's a characteristic pattern. So if we go back and forth in history, these distributions change in a characteristic way. And we can try to quantify this by a single number that we could call tonal complexity or fifth width or whatever. It tells us something about the harmony, and we can do this on a local level, for example, for single pitches, and on a global level for whole pitch class distributions. So the extreme cases would be a single pitch that would have complexity 0. We have all pitches sounding at the same time, complexity of 1, and we have everything in between, which is complexity between 0 and 1. And a simple way is to use some circular statistics, project these distributions into this circle of fifth space, and just compute the sum vector, so the vector sum, take the inverse of its length, and then we get value which has the opposite behavior, because in this case we have the maximal length, here we have the minimal length, so we invert it. And we use such measures to analyze larger corpora. For example, this one, still based on my PhD work, 2000 instrumental pieces for piano and orchestra across 350 years of music history. And we can project this tonal complexity onto the timeline using composition dates, if we have them, or at least the lifetimes of the composers, and get some tonal complexity curve. And this is quite interesting. So if you look at the global curve, that's the one that captures these full piece pitch class distribution. You see it goes up more or less all the time with some smaller decrease after Bach's death, and some stronger increases in the 19th century and around 1900. It's also interesting to look at the relation to the local complexity. So that's if we first compute these values on each frame and then average. So it tells us something about how complex are the chords used. So for example, in the 19th century, this local complexity is mostly constant. There are more or less the same chords used, while the global complexity, so how these chords are arranged over time, the keys, the modulations, are becoming more complex. Around 1900, when the atonal composers like Webern or also Schönberg started contributing, all of them start to rise. Now, this is an interesting finding for instrumental music. We had some cooperation with a music publisher for choral music, which let us extend this to choir and sacred music with an even larger data set, almost 6,000 tracks of choir and sacred music. And this spans even more time, going back to the mid-16th century. And we found a quite different pattern. So if you compare it, we have the peak around 1800, and then much less is going on. At least we don't see this strong increase. And that's interesting because that means composers probably had to compose differently for singers. Very complex harmony that you can do with a piano or an orchestra seems to be challenging for choirs or solo singers. So we analyzed this by taking the two corpora together and tried to plot a vocal complexity against an instrumental complexity. And yeah, so the green line is the vocal and the red line is the instrumental complexity. And interestingly, this relationship changes over the years. So around the classical time, church music was the more complex one, which is also known in music history, for example, by the use of polyphony. They still composed with fugues and other counterpoint structures, as opposed to symphonies and string quartets, which became a little bit more simpler, also dedicated more to the general public. And then during the 19th century and especially the 20th century, this relationship changes. So the instrumental music becomes more complex, while the vocal music more or less stays the same. Yeah, and finally, with a PhD student of mine, we did some interesting research relating this evolution of the whole corpus to the evolution of individual composers, where we have a good coverage of their whole work. And we find interesting pattern for that relate to the overall evolution in interesting ways. So for example, Heinrich Schütz in the 17th century composed very much like his contemporaries. So he seemed to follow his general style or also influence his style, while Bach, for example, in some phases was really ahead of his time. So he composed in a more complex way around 1720 to 30, and then later the whole evolution took up to him, catched up. And the 19th century have an interesting case for Franz Liszt, who composes much more complex, goes a little bit down later, but is clearly special regarding his style as compared to his contemporaries. And this can be interesting starting points for musicologists to look which works are contributing to that. How about the closer network, like the teachers and students of a composer, and so on. Yeah, with that, I'm at the end. Sorry for the little overtime. I think it became clear that there are different things that need to become, that need to come together. It's very fruitful in our experience that we don't see these things separate, like not that a musicologist is developing a tool, that an MIR researcher is developing a tool that a musicologist is using just as some software and as a tool for enriching his work, but it's much more fruitful to really develop these algorithms together, include the knowledge of the musicologists to develop the tools in the right way, and also publish together, talk about the musicological interpretation, because that creates a deeper understanding of all sides and makes the cooperation more fruitful. And with this, we can hopefully see much more nice corpus analysis in the future, and of course also on more styles than just classical music. But I mean, the experts on that are here in Barcelona, especially. So I hope that was a little bit inspiring, and I'm really happy to take your questions now.
Okay, thank you.
Thank you very much. Amazing talk, Christof, and very impressive work. You were perfect on time, so don't you worry.
Okay.
Are there any questions in the room? Or online? I have a couple of questions that I could start, and then yeah. So something that I'm quite interested in is like this complexity that you were referring to in terms of differences between annotators. We experienced that recently in a work with Andrea on chord annotation, and I think that open up a lot of interesting research paths, because this agreement actually is a very could be a nice opportunity to learn from, right? But there are technical challenges on how to do that. The way you address this kind of things, it's really interesting, and I'd have a look at it. Well, we yeah, in the work that Andrea did, we had a look on trying to understand where do discrepancies come from, and they are not actually random but have a musical meaning, let's say. And one recent work that I was very interested into is it was presented at Izmir, and it was by a student from from Slim Aziz and Jofra Peters. They were working on beat tracking, but considering different hypotheses, right? So ambiguity could be modeled by like considering different valid hypotheses at the same time, which somehow relates to a stream in machine learning, which is multiple choice learning. So I was wondering if I mean, if you happen to be thinking of these problems from that perspective, or what are your thoughts on that?
Yes, that's a very good question, and I think we could talk about that for quite a long time. I mean, we are looking into chord recognition in this respect as well. So I think there are two major sources that play into this. One is the hierarchy problem. So just as for keys where people disagree if there is a modulation at all, it's the same for chords. So if you like give either an annotator or a chord recognition system the information, here is the chord boundary, they would agree on the chord label much more than if they choose the boundaries themselves. Because I mean, consider an extreme case like a Beethoven sonata where we have just triads. Of course, each one itself is some chord, but it's not the harmonic structure. And between these extremes, again, you have different levels that you could consider a chord. One are closer to what the musicians are doing. One are closer to an overall harmonic progression analysis. And neither of them is more correct. It's just that the term chords is used again for different things on different levels. And we have started to do some experiments, and this segmentation oracle, so to say, give the ground truth chord boundaries regarding some reference annotation, and then let the system predict the chord. That helps to raise the level of correctly recognized chords regarding some reference annotation quite a lot. And the rest of the ambiguity is often similar as for the keys, is musically close. So it's probably a different label. So if you go for standard metrics, root-based metrics, you consider them to be an error or a mismatch. But if you just compare the pitch classes that are parts of these labels, they would overlap to a higher degree. So it's usually whatever, 2 of 3, 3 of 4, or something like that would overlap. And then again, which one is the root node? That's often a question of music theory definition. And I think that's the answer for the more musicological direction. So if you want to keep an interpretable representation, for more ambiguous problems like what is a similar timbre, what is a similar style, and so on. There, I think the approach that you mentioned to consider some multiple choice learning or some more abstract representation learning is an interesting direction. And that's something we want to explore in the next years, because the cross-version data is very interesting. So even if we don't know what's the timbre at a certain situation, or what's maybe also the chord or the rhythmic complexity, as long as we say this is a feature that is already given by the score, so is indicated by the composition, we know that it's the same for all versions. So if you have two orchestra pieces that are aligned to each other, we know at the corresponding positions, it's the same instrumental timbre. And this lets us disentangle the dimensions and learn these dimensions without having to label them, because labeling is tedious and also sometimes problematic because of the ambiguities. So we can let the system learn to have the same output, even if this output is abstract and may involve multiple choices. But it should be the same multiple choices for two versions. And I hope that we can contribute with robust representations on something like that, also using the cross-version idea.
Thank you. Thank you very much. My other question relates to the, well, I'd like to start by praising the efforts you did on releasing datasets. It's interesting that you mentioned that in some cases it took more than 10 years and to collect and prepare this kind of datasets. Yeah, I think it's an amazing contribution to the community. I was wondering what kind of challenges there are, like for instance, the work that you did on scores, I guess. Do you have permission for releasing this kind of information? Are there any thoughts that you may share on the challenges on releasing data sets like this?
Yes, it's different for the different data sets. Usually we rely on public domain sources, like the score versions that are also on IMSLP and all the known platforms. And there are some copyright regulations on age and of the publication of the release that apply there. Same as for the audio, there is, I think, a rule that everything recorded before 1963 is in the public domain. And luckily, our compositions are free because they are old enough, but also the performances need to be free. And same for the score. So, for example, for the Wagner, it's not a full score, it's a piano reduction. So it's not all orchestra instruments, but just some summary, which was released in the 1920s and then digitized. So this is an open version. And what we did some OMR and a lot of manual correction, or our musicology partners did that, to have it in symbolic music XML and so on format. Similar for Schubert. In other data sets, we rely also on public scores from the ISME community. So we are working on the Beethoven string quartets. There we use the scores released by Martin Rohrmeyer's team in Lausanne, the ABC dataset. So we try to use as much as possible the effort that has been done in our community already.
Great. Andrea, do you have a question?
Yes, thank you. So thanks a lot, Christof, for first of all for accepting the invitation and also for the great talk. I have a more, I would say, methodological question I wanted to ask you, which is on the terminology first, but also on the epistemology of computational musicology. And because we called this special interest group computational musicology, but there was kind of a lot of discussion on whether this is the correct term or not, and also on what differentiates computational musicology to MIR, because for example, if we tackle tasks like key estimation or chord estimation, they're probably they belong as much to computational musicology and to music information retrieval. On the other hand, in your talk, you were highlighting interpretability of the results. And also discussing these cross version data sets, you were showing how the variability of annotations and these inter-annotator disagreements that affects most of the musicological types of annotations. And you were showing different ways of visualizing and kind of embracing this type of diversity in annotation. So what do you think is the difference between MIR and computational musicology? Is just about a research question, is the methodological approach, or is more in how we look at the results? Meaning that we, in computational musicology, we are probably not really interested in having the best results, but rather in truly understanding them?
Yes, that's a very good question. I mean, I hope ISMIR is always or will always be as inclusive as possible, and that computational musicology is always also has a home at ISMIR or some overlap. Of course, there is a continuous scale from what algorithm you are developing on local key estimation, on music transcription, and how you apply it in computational musicology. But I would agree it's on the way we present, interpret the results, and how we have to design our methodology so that it is useful for musicology. And let me give an example, like chord recognition. It's first of all, we can define it as a machine learning or technical task. We have some output, we have some input. Architectures will play a role and so on. There's not that much work been done. Thanks to you, there has been a paper this year at ISMIR, but last year's it was very rare. And I think one reason is that given all these challenges of evaluation, it's hard to really measure improvement in the sense of one algorithm is better than the other one. But there has been a lot of chord recognition around in the usage domain. Like it has been used at Chordify, at Musician, and all these music education startups, for example, because the technical performance is way good enough for delivering chord symbols to a hobby guitar player that wants to play his favorite songs. And there has been nice work by Vincent Kobs, for example, in his PhD, where he said, let's use some more abstract chord representation and then decode it so that it is optimal for a certain player. So for example, the level of expertise could be switched so that some complex chords are allowed and others not, and so on. So it's more about how to make use of this technology for a certain application. And computational musicology is such an application with the specific demand that results need to be interpretable first. I mean, some 128 dimension embedding is not really interpretable. And also bias is more of an issue. I mean, for Chordify and a hobby guitar player, as long as my system works for standard pop music, more or less, I'm probably fine. For musicology, if I train on the Beethoven piano sonatas and the Beethoven string quartets and the Beethoven symphonies, and then I want to do analysis from 1500 to 1900, of course, that's not an acceptable methodology. And then, of course, I can try to build a chord data set for 400 years of music history that is balanced, and it will be a big, big mess and take 10 years and will never be perfect. So we can then learn some representation, but in my experience, it's a better way to measure something that is much more objective, like music transcription task, like pitch classes, and then just map to probabilities and leave the ambiguity open. And that at the same time avoids many of these biases. So these visualizations, as I showed them for the Wagner, they are a nice way. And of course, it's not straightforward for a musicologist to read that, but you can explain it to them in a limited amount of time. If you work together for longer, they become really good at exploiting this and they know about the limitations. And if you deliver a tool, if you give them an algorithm and say, this algorithm can detect major or minor chords, maybe up to 85%, it's often a problem because then they start using it and they get a result that they don't expect and they say, the algorithm is wrong here, it's not a useful tool. But maybe there were just two different chords that had a similar probability and the system had to decide for one of them. But the information that these two chords have a high probability is actually describing the musical situation much better. And trying to come up with good ways to resolve this and good interfaces that allow for capturing this complexity of analysis is one of the important things. And we have made very good experiences with visualizations of all kinds there. And by the way, this then also blends into the broader computational humanities community, which of course doesn't know about pitch classes and keys. Like for example, there's a very nice conference since a couple of years, computational humanities research. But what you find is that they have very similar problems in their field. Like they all come up with representations similar to those ones, to trying to measure some properties over history, try to find also statistical methods. How can I deal with missing work dates? And it doesn't matter if it's the composition date of a symphony or if it's the date where a fine arts work has been drawn or a novel has been written. And that's very fruitful from a different perspective. So yeah, hope to have answered your question more or less, but I think it's the way how we use the algorithms and how we design the interfaces is the crucial difference, I would say.
Perfect. Thanks a lot for your perspective on this.
Very nice. Are there any other questions, either in the room or online?
I have a couple of questions, if I can. So, thank you very much for your speech. I was wondering, you said that you don't really know. Okay, it's a joke. We cannot trust the annotator who said in the lead that you showed us, it was all A major, while other annotators say, no, it's A minor and the E major. So, okay, we know that music is complex and we need to trust the ground truth that they provide us. But the opposite, I was wondering, do the musicologists trust the model, or did you do any kind of surveys of the users that use these models? How do they use these tools? Do they find it useful, or do they point their fingers on some real problems that you are trying to solve? And a follow-up question, I'll do both and then leave you space, is I ask that because there are already a lot of old musicology theory, not about computational, but you know that in the 20th century there was the Ian Bank book about audio analysis styles. So you already have a lot of models that are applicable, for example, and don't rely too much on harmony. For example, the Allen Forte set theory, or what else? The Youngblood entropy approach, or there are well, you know, there are many approaches to representing this kind of analysis. And I was wondering, did you consider, first of all, are the musicologists using these old approaches, or did you consider integrating them into your machine learning models? I suppose that in the neurosymbolic approach of deep learning, it would be interesting to combine both of them. So the old musicology approach and these chromogram, etc., or raw audio analysis. What do you think about that?
Yeah, that's a very big question. Let me start with the first one. So in the case of the Wagner analysis, it was a process. So we started with chords, then went to these scales, and then there were situations where musicologists said the model is wrong here and there. And then we tried to teach them how probabilities are working, and that the model cannot be wrong because it does not actually decide. It does not recognize a key, so it's kind of a very weak model regarding what a musicologist would put in interpretation here, for example, on a key. That's a really difficult task and demands a lot of expertise. But this objectivity or neutral perspective is also helpful, because it's not more, but also not less than a direct mapping of the pitches that are in the score. And we saw that it's very similar to the ones from the score, or that the musicians are playing, to the 12 diatonic pitch class sets. And this is an unusual way of thinking, but they can understand it because they know what a diatonic scale is. And they know that some music passages, especially in Wagner, are not at all diatonic. And they learned how to interpret this, and that this probabilistic view has its advantages. And I think that's a process, and that's what I refer to, that it is necessary to talk to each other. If you would provide this as a tool to a musicologist which has never talked to an MIR researcher or a computer scientist, they would not find it useful. So you have to educate them a bit. But I think for many of our questions, there is not really a way around it. Regarding your second questions, other modeling approaches, I mean, of course, there's a big field of other computation approaches, models, also, of course, tonal models, general models on musical style. It's always difficult because in order to measure, to visualize something, you have to restrict your output space somehow. I mean, for example, in the case of our tonal complexity, we had to reduce it to one dimension because we have the timeline as the other dimension, and we just have 2 dimensions for plotting. Of course, this is not the full truth. And of course, tonality as a whole is just a very small part of explaining musical style and how music evolved. but it's a part that is at least interesting enough. And I mean, this is a simple but very interpretable way. One can also go towards higher dimensional features. I did that in my PhD, trying to do classification of historical periods and composers. You then have several hundreds of features and you project them into a more abstract space. I think this is much more expressive, and the computational musicology community likes this approach, but a traditional musicologist would struggle even more by interpreting this, whatever first PCA dimension or cluster weight and so on. So it's always a trade-off. I think you can do much more expressive things, but then you will also address a smaller part, at least currently, of the musicology community that is capable and also willing to understand that.
Thank you very much.
Amazing. Okay, so if there are no other questions, we should thank again Christof for this amazing talk and the interactions, and see you next meeting.
Yeah, thanks a lot for the invitation. It was bye bye. Have a good time.
Thanks, Martin.